Okay, so we're going to continue actually sketching some surfaces in this little segment. And I want to remind you that a surface would be a two-dimensional object if it was just a flat plane. But included in surfaces is the sphere, which we've already seen, and the equation of a plane in 3 dimensions using some vector knowledge. And then we already sketched what's called cylinders, something that has a two-dimensional cross section but it extends forever in the third dimension. That would be an upside down parabola, extends forever. And then in the last segment I was using the GeoGebra tool to show a variety of other shapes with the promise that I would do some follow-up. Well, so that was a higher quality image. This will be a lower quality image, I would be guessing, or samples thereof. So we were looking at what's called different types of quadric surfaces. Think quadratic or second power and variations that include x, y, and z. And the first type was the category of paraboloids. I would rate this as a pretty important one in my classroom, one that's easy to manipulate and study, but definitely is in the direction of 3 dimensions. A satellite dish would be sort of an example of a type of paraboloid. So an example of a paraboloid would be the z equals x squared plus y squared, and I walked through it in the last segment how to think about plotting points and things. You were asked to sort of give it a try yourself, but if you're in my classroom and you're expected to draw it, you could simply just draw a portion of a parabola and then use an arc here and here to sort of pretend it has a 3-dimensional cross section, and the z equals model opens in the z-axis direction, and then in the standard orientation I've been showing, we would call that the x and y axis. You have to call this a sketch. Alright? It's a sketch. There's no scale on here. It looks like it's bent a little bit, but it does represent the location, and the expectation for me is if you saw one of these modeled, you would know that's the algebra that goes with it. You know that relationship. If it were of the form, let's say x equals y squared plus z squared, I also counsel my classroom, don't feel tethered to this standard orientation of the axes if you're asked to draw it yourself. You could duplicate the shape exactly the same, but simply label this the x-axis, and then it doesn't really matter here which one is y and which one is z, because these are circular cross sections that there's symmetry there. If you would like the challenge of drawing it oriented this way, I typically draw the picture first and then put the axes on later. So you could try to draw it opening in the x-axis direction, but I'm not very good. Alright, nope, it would come out this end and go out that end. And we've got X and Z and Y. And that's already a horrible picture. I'm using pen and I can't erase. But if you submitted this as a sketch, I would have to give you credit. Now we can make little variations, such as if it says y equals x squared plus z squared plus 2, that should move the graph 2 units in the y direction. So once again, you don't have to try to draw it perfectly to scale. You could attempt to draw it, well, like this. Label that the y-axis, but it needs to be moved 2 units. So that would be x and z. So maybe I would label this as 2 right here to indicate that this graph has moved 2 units in that direction. I don't want this sketching to be threatening. The algebras and the calculus to follow are going to be our primary source of nourishment and exercise. The sketches here are to build that visual aspect of it. This would be a fantastic time to have a 3D printer to be able to model things, or a little bit higher quality software, although GeoGebra does better than my pictures are. Let's look at a couple more before we close this one out. Let's suppose I were to have you graph z equals negative x squared minus y squared. Any thoughts on that? Well, that's right. Think it opens down. Now, I might not show the other arc. I might do a dotted line to say, hey, it's behind this graph. But that would be the z-axis, and that would be the y-axis, and that would be the x-axis, and the vertex of the paraboloid is at the origin. A more interesting model might be something like z equals 25 minus x squared minus y squared. Now that's more interesting. I'll close that arc again, opens down. You can decide whether you want that there or not. And we would let that be the z-axis. Now, what's that 25 do? Well, it raises the graph 25 units up in the z-axis direction. So the z-axis comes down, there's your origin, and there's your x-axis, and there's your y-axis. And we already know that it has circle cross sections, but I wonder how big that circle is. I wonder how big that circle is. So what is the radius on the xy plane? So that's not a full sentence in writing in English, but the thought is there. It's kind of like those are the key phrases. What's the radius right here? Anyone want to make a guess? Well, it is 5. So if z is 0, you would rewrite this as 0 equals 25 minus x squared minus y squared. So therefore, x squared plus y squared equals 25. That's a circle. Radius is definitely 5 units. Later in the course, we're going to be looking at the calculus that will find the volume of that shape, or actual surface area of that shape. If we had a density function, we could find the mass and the center of mass of that solid object. Okay, a couple more really fast. One type that I introduced in the last segment was called an ellipsoid. So perhaps it is x squared over 4 plus y squared over 9 plus z squared over 25, I'm going to use 25 again, is 1. It's going to look like a type of ellipse no matter which way you view it. So you could theoretically try drawing axes first, but I think I would do it this way. It's bigger in the z direction, and it's not as big in the other direction. So let me just draw one that looks taller up and down. We'll put a belt on it and say, well, that's the halfway point. And there is your y-intercept, and there's where x-axis comes out there. And there's your z-axis. And again, not a grand scale, but it is going to hit 5 units up and down on the z-axis, 3 units in either direction on the y-axis, and 2 units in the x-axis. Now I'm not reteaching about the ellipse, but this should bring back some recollection from some mathematics before calculus. All right. I kind of feel like I need to do this one. Okay. Z equals y squared minus x squared. For this particular term, you need to check with the instructor whether you're going to need to know how to graph this one. It varies from term to term at school. So the sketch is called, well, I won't even write the name here, the hyperbolic paraboloid, sometimes called a saddle graph. This particular one happens to have this sort of a shape to it. There is the z-axis, and there is the x-axis, and there is the y-axis. It is very much not to scale, but I can show you that if y equals 0, this is z equals negative x squared, which is a parabola that is in the xz plane. It's not on the paper, it's more like this. And if y equals 1, you get z equals 1 minus x squared. And so when you go in the y-axis direction, the vertex is 1 unit up. And if y equals 2, then z equals 4 minus x squared. So that would be 4 units up in that direction. But the parabola opens sideways. It's not too difficult to draw, but it is maybe difficult to rotate around for people. I have been known to get paralyzed in a live classroom setting on this graph when people are actually watching me. All right, there's some sketches. Get to practicing, okay? Till next time.